So let's talk about Archimedes' method for approximating pi. Let's just real quick review what pi is. So if I have a circle with a diameter of d, it has a circumference, which I shall call c, which is the distance all the way around the circle. Pi comes up because the circumference, as it turns out, is pi times the diameter of the circle. And pi has a known value of approximately 3.14159, and so on and so on. How can we try to approximate pi? Well, what did Archimedes do? Archimedes imagined inside of his circle inscribing a regular six-sided polygon, a hexagon. Now, of note is that Archimedes never actually came up with a numerical value for pi, because to him it wasn't a number. And in fact, all he was trying to do was figure out how the circumference relates to the diameter of the circle. Let's think about how this hexagon allows us to approximate pi. So if we look at it, to a first order approximation, this length is less than this length, but if I drew it better, it would be fairly close. Similarly, this length is approximately this length to a first order approximation. And this length would be similar to this length to a first order approximation, and so on and so on. And if I were to do that for all six sides, approximate all six of these sides, or get the values of all six of these sides, then approximate the circumference as the sum of all of them, then that gives me a rough approximation for the value of pi. So, let's think about how we can get that. So I'm just going to draw this in a bigger form. And if I start at the center of the circle, which is also the center of the hexagon, I'm going to create a bunch of triangles. The term for this is I'm going to triangulate the hexagon. Now, this is a regular hexagon. So all of these edges on the outside, which I'm going to mark in green, all of these have the same length. That's what it means for a polygon to be regular. All of its external edges have the same length. That's one of the criterion. The other criteria is that all of these angles are the same, but we don't particularly need that here. What we do need to note is that all of these internal angles are going to be the same. So each of these angles, let's call theta. Let's see what that is. So we know theta plus theta plus theta plus theta plus theta plus theta. So it's the sum of it's taking one theta from each of these triangles and adding it all together. So that's equal to 360 degrees. Now if I take 6 of something and add them all together, then that's equivalent to 6 times that something. And so if I divide both sides by 6, we get that theta is 60 degrees. So, if I just draw one of our triangles here, and I will draw a green side so that we know where we're in reference to. So this angle is 60 degrees, But one other thing to note is that each of these internal line segments, each of these guys, is, on one hand, an edge of the triangle. On the other hand, each of these is the radius of the circle. Now, for ease of calculation, I'm going to make this circle have a radius of 1. So each of those red segments will have a radius of 1. And here comes the insight. So, because this angle is 60 degrees, these two angles together must form 120 degrees. Because a triangle has 180 degrees. And so I'm taking off a 60 degree angle, I get 120 degrees. But because their opposite sides are the same magnitude, that means these two remaining angles must be of the same size. So, to get each of those, I just take 120 degrees, divide by 2, and we get 60 degrees. So each of these angles is also 60 degrees. So we must have an equilateral triangle, making this side length be 1. And we can do this construction for every one of our 6 triangles. So, that means that our circumference, which I'll call C the circumference of a circle, and then I'll use C sub n to represent the perimeter, the sum of the outer edge lengths of the n-sided polygon. So in this case, we just found C6, the perimeter of the 6-sided polygon. It's going to be 6 times the green edge, because I'm just taking 6 of them and adding it together. So we get 6 times 1, which is 6. Now, the goal behind that was because that gives us a way to approximate to a first order the circumference of the circle, as I demonstrated over with this circle on the left. So this is approximately C, but we know that the circumference of a circle nowadays is pi times the diameter, but the diameter is twice the radius. So in this case, we just get 1, and then multiply by a 2, because we have to multiply by 2 times the radius. So this is 2 pi. So we've got 6 is approximately 2 pi. So pi is approximately 3. And as we can see, that is a very rough guess for the value of pi. And for most casual calculations, that'll usually be good enough. But I want to get a little closer. So Archimedes had a clever method for doing so. And again, he didn't actually numerically approximate pi. He just tried to find it in terms of the diameter of the circle. We're taking it one step further using modern symbolism. So I'm going to real quick draw my hexagon again. Okay, now I want to try to take each of these outer edges and find a closer approximation of this arc length here. So what'll happen if I split this angle in half, draw all the way out to the edge of the circle, and then connect each of these with a straight line. Here, I'll do that in red. Nope, that's not red. Something like that. And I'll go ahead and go back to green for the original edge of the hexagon, because that'll come in useful. So I've split this angle in half. So what does that mean? That means that this triangle and this triangle are the same triangle, because this angle will be the same. And then this edge and this edge will be the same. And they share a side, so that side length has to be the same. So what I'm going to do is I'm going to draw just one of these triangles and blow it up a little bit. So we know this whole length is a radius of the circle, and it's 1. Because that's this side length that I'm going to mark in blue. That's not blue. This is blue. That's a radius of the circle, and so is this. So both of those lengths are 1. Now, we know the length of the green edge here. We know this length from the hexagon. That length was 1. So since I split it in half, this length is going to be half of 1. So the length of this green side here is 1/2. Now, due to the geometry that I've used to construct this ends up being a right angle. And so, the thing we want is this thing in red. So I'm going to call this S12. And the reason I'm choosing that is it just means side length of the 12gon. Because once you go past about 9 sides, most polygons don't really have a name that everybody's going to remember. So 12 sides is usually referred to as a 12gon, or if you really want to be fancy, the dodecagon. Do here meaning 2, and deca meaning 10. So 2 plus 10 is 12. Just as a small tangent. Anyway, we want this red side. But to get that, I'm going to need to figure out this side and this side. So I'm going to call this length here X, and this length Y. And let's see if we can find some relationships that would be useful to us. So if I look at this right triangle here, I can use the Pythagorean Theorem, because we know that that side length is 1/2. And we get x squared plus 1/2 squared equals 1 squared. And so we get x squared plus 1/4 is 1 squared. So x squared is 1 minus 1/4. And if we treat this as 1/1, I want to get a 4 down here. So I'm going to multiply by 4 on both the numerator and denominator. That's the same as multiplying by a total of 1, which I can do. And so we're going to get 4 over 4 minus 1 over 4. And now that I've got the same denominator, I can subtract straight across on the numerators. We get 3 over 4. So then, if I want to get x, I just take the square root. So x is square root of 3 over 4. But I can break this up as root 3 over root 4. And root 4 is just 2. So we just get root 3 over 2. And the reason I decided to take the positive square root here is that we know x is a length. So x cannot be negative here. And this value is definitely less than 1. So we've definitely satisfied the geometric conditions of this side length here. Now what about y? How do we get that? Well, we've got this right triangle to use now. So we've got y squared plus 1/2 squared is equal to s12 squared. Now the problem here is that I have two unknowns. Two things I don't know. I don't know y, and I don't know s12. So let's try to remedy that. If I knew what s12 was, then we'd already be done and I wouldn't be going through this. So that means that I must have some kind of trick up my sleeve to find y. And I do. So notice here that the whole distance from this point to this point between these 2 points is 1. But also, that distance is x plus y. So we know x plus y must equal 1. So we know y must equal 1 minus x. So if I take the value of x that I have, I've got y equals 1 minus square root of 3 over 2. Okay, let's go ahead and work with that. So take that, plug it in there, and we get 1 minus square root of 3 over 2 squared plus 1/2 squared is s12 squared. So let's take this, go down, and keep working with it. So what's 1 minus square root of 3 over 2 squared? Well, I can rewrite it as 1 minus square root of 3 over 2 times 1 minus square root of 3 over 2. And so I'm going to use the FOIL method for multiplying binomials. So I'm going to multiply the first two together. We're going to get 1. Then we're going to multiply the outer two together. So a 1 and a negative root 3 over 2. So minus square root of 3 over 2. And then the inner ones, that's the I, we get minus square root of 3 over 2 and a 1. So we get another one of these guys. And then we get the last terms. So negative square root of 3 over 2 times negative square root of 3 over 2. So a negative times a negative is a positive. And square root of 3 squared, or times itself, is 3. And 2 squared is 4. And so if I combine all the like terms, we get 1 plus 3 over 4. That's 7 over 4. If we follow the same method as before when I found x squared, then we get minus 2 times the square root of 3 over 2. But that simplifies to square root of 3. Okay, we're almost done. So that's what this term here means. That's what our y squared was. Now, remember we had 1 minus square root of 3 over 2 squared plus 1/2 squared is S12 squared. And S12 was that red edge of the dodecagon that we're after. So now I'm going to plug in the thing for this that I have now. I'm going to simplify that a little bit. And hopefully it turns into something nice. So this we found was 7 over 4 minus square root of 3. And then we get plus the square of 1/2. Well, that's 1 over 4. We get S12 squared. Now let's add these two fractions together. So because they have the same denominator, when I add them, I can just add the numerators and keep the denominator the same. So we get 8 over 4. But 8 divided by 4 is 2. So what that tells us is that S12 squared is just 2 minus the square root of 3. So S12 is just the square root of 2 minus the square root of 3. So if we go back up to our diagram, we just found the length of one of these red edges. But because I have constructed those are the edges of a 12-sided polygon. So if I were to break all of these hexagons, all of these hexagon triangles up, like we did the first one. And again, terrible drawing. But you see that we end up with a 12-sided figure. So and this is a regular dodecagon, 12gon. So what we end up with is we're adding together 12 of that edge length that we just found. So I'm going to call that C12 for the perimeter of the 12gon. And that's equal to 12 times this thing that we just found. And if we take that, we get approximately 6.2117. Now that doesn't look like pi, but remember, we're approximating the circumference of the circle. The circumference is 2 pi r, where here I've set r to be 1. So C12 is approximately C, which means that 6.2117 is approximately 2 pi. So pi is approximately half of that 6.2117, which is 3.106, which is closer than the 3 that we got before, because remember pi is about 3.14159, and so on and so on, as the actual value. But here we've got two decimal places after the decimal point of accuracy. So if you were to keep doing this method of splitting your previous triangles in half and then computing the new edge length and then multiplying by the number of edges you have, and then equating it to 2 pi, then of course dividing by 2, you can get closer and closer approximations of pi. So the next step would be to find what C24 is by finding S24, where this is the side length of the 24gon. And then this would be the perimeter of the 24gon. And this method you can apply as many times as you want. Archimedes himself, he applied this up to 96 sides. So he went from 12 sides, he went from 6 sides to 12 sides to 24 to 48 to 96. So he just kept doubling the number of sides every time by taking the previous triangle, splitting it in two, and then finding these new edge lengths. And you get to double the number of sides every time.